All right, should we get started?
Yep, go ahead.
Cool. All right. So as I said, this is a very similar to the one that Dan did last week. Instead of the circles intersecting at two different points, the only difference is that the circles are touching at one point. So the proof is essentially the same. So if two circles touch means touch at one point, share the same tangent at that point, then they don't have the same center. Then they don't have the same center. Okay, so the picture, the only difficult thing this week, I think, is that I'm gonna have to draw these pictures. I'm gonna have to draw two circles. I think. Here we go. One, and I found that if you start here, you have more of a chance of success. There we go. Kind of okay. And so we're gonna assume that we have a center. Well, I'll kind of say what these things are in a bit. So the point that they touch, we're gonna call C. We're gonna extend a line from F to C, and then we're gonna extend a line from F to somewhere else. Okay, and we're gonna just label these points E and B. I haven't said what F is yet because we two circles, right? Which center is it, right? So we're gonna let proof. We're gonna let C be the point where the circles touch, and let F be the center of one of the circles. So one of them, doesn't matter which one. We can do this by proposition 3.1, right? Where it allows us to find the center of any given circle. And we're going to assume that F is also the center of the other circle. So that's the assumption. I'm going to contradict this assumption, and then we've got our proof. So we'll assume that F is also the center of the other circle. Okay, then I'm going to move to the other board. Actually, I don't have to move. And we're going to draw a line from F. Line from F to the other circles, to the circles. I'm being a bit imprecise here, but I think we can make this precise, right? In the text, Euclid just goes draw a random line or choose some random point, draw a line through it. But we've got the line FC, right? We can just construct a line that's perpendicular to FC. We want to be completely non-random about this, right? We can just do it, right? I think we have a proposition that allows us to do this. I forgot the number. I'm pretty sure we can construct perpendiculars. Yeah. So I'll just put the right angle there. So now we have a line. FC is predetermined, right? And then we draw a line perpendicular FC, intersecting at, I guess, what did I call it? E and B. That's weird. Okay, E and B. And from here, I mean, the proof is the same, right? Like, since, well, I'll just say it, right? We have FC equals FE because F is the center of one of the circles, the circle that E is on, and FC is equal to FB because we assume that F is also the center of the circle that B is on, right? But this is impossible because FE is part of FB. But this is impossible since FE is part of FB. Okay, and we're done. I think, Dan, we can do the same thing to resolve the thing that you were on about last week about choosing random point, right? You can just copy perpendicular, and then you've got a line that is defined completely without random choice.
Yeah, that's good. I didn't think of that.
Cool.
All
Now
right.
it's I think we've got 20 minutes.
Okay. Yeah, we can do it. Okay. Proposition 7 says the following. Let me draw a picture first. All right, so let's first consider a circle with diameter AD. And center E. And we're going to pick a point F, which is not the center, but lies on the line AD. So if on the diameter of a circle, a point is taken, that's F, which is not the center of the circle, and from which we're going to draw straight lines to the circle. So we're going to think about the length of those lines. So here's a few possible lines. You could draw a line from F just along the diameter to A. You could draw it to D. You could draw it to somewhere in between. Or you can draw it on the other side, but of course that's symmetric. And we notice that there's a relationship between the lengths. Sort of intuitively, it's clear that's the longest possible such line, that's the shortest, and that the others fall into a sort of predictable order. And that's what I'm about to say. I won't say it exactly as it's written here because it's a bit of a mouthful. The greatest will be the line through the center, that's FA. The least is the line on the diameter not meeting the center, that's FD. And for the rest, so any line from F to the circle that is not on the diameter, the nearer to the straight line through the center. So if you have two such lines, the one which is on the side closest to FA is greater. In length. Okay, so let me fill in some points. We'll just pick some points B, C, and G, and connect these to F initially. All right, so the last sentence is saying that FB is greater than FC because FB is nearer to the straight line through the center, that is FA. So FB is greater than FC is greater than FG. And there's one more statement. Among these straight lines from F to the circle, the only way you can get equal lengths that are coming from different lines are if you take them on opposite sides of the diameter. Yeah, the way it's written doesn't actually seem correct to me. It says the least line, but this doesn't really make sense. I think this is the correct statement. All right, proof. Okay, I won't repeat the construction. We've gone through the relevant labels. We say FA is greatest. FD is least. And FB is greater than FC, which is greater than FG. Remember, greater here means that we have a proposition that allows you to take any line and draw off on a given line a segment equal to that other line. So that's how you compare what's greater or what's less. There's no numbers involved, unless you call those lines numbers, which is reasonable, but that's book 4 or whatever. Okay, so we're going to join all the lines that I did join, but we're also going to now join some additional lines because we're going to reason about all this using triangles, obviously. So BE, CE, and GE. So we're going to connect everything to the center. Why? Well, because now we have 3 triangles which share a common side, namely these radii, and then their other sides are in common, that's EF, and the third sides are the things we want to compare. And we know that we can compare lengths by comparing the angles that they subtend. And clearly the angles they subtend have the right relationship. And that's basically the proof. Okay, since in any triangle 2 sides are greater than the remaining one, so that was proposition book 120. If I take EB and EF together, as I add them, they're greater than BF. But AE equals BE, they're both radii. So EB, so AF is greater than BF. Check this makes sense. So AF is greater than BF because EF is greater than what? EF is greater than BF, yes. Oh yeah, okay. So that's just the same statement because AF is AE, comma EF, all right? Since BE is equal to CE, and FE is common, the 2 sides BE, EF are equal to the 2 sides CE, EF. Check. BE, EF are equal to CE, EF. Yeah, that's what I said earlier. Right now we just compare the angles. But the angle BEF is greater than the angle CEF. therefore the base BF is greater than the base CF, which is proposition 124. Okay, so that's I feel like kind of missed the statement about AF being greater than BF. It's this, not quite this. Oh no, I did say that, right? AF is greater than BF, right? And now we know BF is greater than CF for the same reason. CF is greater than GF. Now we need to compare GF to FD, right? So since GF FE are greater than EG, yep. And EG is radius, so that equals ED. We have GFFE greater than ED. And now we can subtract FD from both. What? No, FE from both, right? Gives GF greater than ED minus FE, which is FD. Okay, so this proves the ordinality relationship between all of these lines. Now it remains to prove the final statement about the only line matching, say, the length of FG is the one that goes below the diameter. So, and well, it's sort of, it exists and it's also unique. So let's prove that. Okay, so claim from F, there are precisely two. Sorry?
You want to walk the orca over?
Oh, thank you, yeah.
Cool. Thanks.
Is my head out of the way?
It's completely blocking.
How's that?
No, it's good.
Okay. From F, there are precisely two lines meeting the circle with the same length as FG. FG itself and the other FH. So I need to construct H. Okay, so here's the construction. So let the angle FEH be constructed. So remember, we have a proposition that allows us to, given any rectilineal angle on a line, construct on that line sort of a copy of that angle. So that's what we're doing. So let FEH be constructed equal to the angle GEF. And that was 23. So back to the diagram for a moment. So we take GEF and we construct that angle again over here. Call that point. So we construct that angle and then we extend the line until it meets the circle. We call that H. And then we join F to H. That's really a bad job. Okay, let me try again. Those do not look equal in length at all. That looks somewhat better. Okay. So we join FH and we claim that FH is equal to FG and that that's the only such line that can be drawn. Since GE equals EH and FH, sorry, EF is common. Sorry, and EF is common. The two sides GEEF equal the two sides HEEF, and they have a common angle. Oh, I did it again.
Cool.
So we have two common sides and a common angle, so the bases are equal. Okay, for uniqueness, that's not what Euclid says, but for uniqueness, let's suppose there were another line. The argument's the same whether or not it falls on the top or the bottom. It can't lie on the diameter, because if it did, then it would either be FA, which is definitely greater, or it would be FD, which is definitely less. And it's basically the same argument in general. So if we were to draw, go back to the picture. If we were to draw some other K and have this line FK be equal to FH, well, either K is closer to A or further away than H. And by the earlier part of the argument, if it's further away, that line must be longer. And if it's closer to D, then it must be less. So it would be a contradiction for FK and FH to be equal in length if their endpoints are different. And if their endpoints are the same, then they're the same line. Okay, so suppose K were such that FK equals FH. Then by the earlier arguments, K and H must be equal. K here being on the same side. All right. So that's it.
Oh, this is shorter than the one I'm going to do next week. But it's similar in flavor, I guess.
Yeah, we're starting to get some more interesting diagrams. I do think it's picking up depth now, right?